very good morning to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering in Institute of Aeronautical Engineering, and I'll be dealing the subject robotics, and my today's topic is discussion on question bank on differential kinematics. That comes under module 3. In the previous session, we have discussed about the question bank in the module 2, and in today's session we will be discussing the question bank on module 3 on differential kinematics. Right? Moving on to the first discussion, that is the first question. Explain the following briefly as applied to robot arm dynamic analysis. That is, we need to explain about the kinetic energy, the potential energy, and the joint velocities. As we all know, what do we mean by kinetic energy? Kinetic energy is nothing but half mv square, right? What do we mean by kinetic energy? Kinetic energy is nothing but half mv square. So, with respect to the robot, how do we determine the kinetic energy? Now, this particular kinetic energy is been associated with the motion of the robot's arm, links, and the joint, right? When we have a robot's arm, links, and the joints, right? This particular kinetic energy comes into action, right? The energy is being associated with the motion of the arms, links, and the joints. Now, it purely depends on the mass of the links and the square of their velocities, right? That here, mass of the links and the square of the velocities. It purely depends on the mass of the links and the square of the velocities. That is, for a robotic arm, the kinetic energy is calculated by considering both the translation motion as well as the rotary motion of each link, right? It has been determined by both translation motion as well as rotational motion, right? That is, the kinetic energy of in the robot will be determined as the motion of arms, links, and the joint, which where the mass of the links will be where the link will be dependent upon the mass and the square of their velocities. Now, for any particular robotic arm, the kinetic energy will be calculated with respect to the translation and the rotational motion. Whereas coming to the potential energy is nothing but mgh, right? That is, the potential energy in the robot arm is related to the position of its component in the gravitational field. Position of the component in the gravitational field means it is nothing but g, right? And it depends upon the mass of the link and their height above the reference, that is mgh. It depends upon the mass, it depends upon the gravitational force, and it depends upon the height about a reference point. As the arm moves, its potential energy changes with the vertical position of its link. That is known as the potential energy. Now, what do we mean by the joint velocities? Joint velocities means what here? It depends upon the speed at which the robot arm joints are being moving, right? Joint velocity is nothing but the speed at which the robot arm are being moving, right? These velocities are crucial in dynamic analysis because they influence the kinetic energy of the system and are necessary for determining the force and torque required to achieve or maintain the specific motion of the arm. This particular joint angle determines the torque and the force, right? The joint velocities determine the torque and the force of the robot's end effector with respect to the motion of the arm. Next, moving on to the second question. Explain the following as applied to a robot arm and also discuss their importance. That is, inertia term, coupling inertia, centrifugal force, components, gravity terms. What do we mean by these particular terms? We need to explain. Right? So firstly, coming to the inertial term. Inertial term means what? It generally refers to the robot arm links to change their motion. That is again both in rotational and translation motion. That is, the inertial term refers to the resistance of the robot arm which links to the changes in their motion, both in terms of the rotational as well as the translation axis. Now, these terms are represented by the linear motion of the with respect to the mass and rotational motion with respect to the moment of inertia. Right? The linear motion is being done with respect to the mass and the rotational motion is being done with respect to the moment of inertia. That is I also we can take. Right? The inertial term refers to the resistance of the robot's arm which links to the changes of their motion both in rotation and the transformation axis, where these terms, that is the linear term determines the mass and the rotational term determines the moment of inertia of the links. Now, this particular inertia is crucial for determining how much is the torque or how much is the force required to accelerate or deaccelerate the arm. Right? The inertia is crucial for determining how much is the torque or how much is the force required to accelerate or deaccelerate this particular robot's arm. Right? Now, it directly impacts the control strategy needed for precise and the stable movement. That is known as the inertial term. Whereas coming on to the coupling inertia, the coupling inertia generally describes the independence of the motion between the different joints of the robot arms. Right? The coupling inertia is used to describe the interdependence of the motion between the different joints of the robot arm. When one joint moves, it can affect the inertia felt by the other joint due to the interconnected nature of the link. Right? When one joint is been moving, for example, when we are moving one hand, what happens? It is interconnected. This particular joint is been interconnected with the arm. So when one joint moves, it can affect the inertia felt by the other joint due to the interconnected nature of the links. This is important because it influences the dynamics of the entire system. Right? This is very important. This control inertia is very important because it influences the entire system dynamics, which makes the control of the multi-joint motion more complex, which is making the joint motion very complex. So, accurately, the modeling of the coupling inertia is essential for ensuring the smooth and coordinate movement of the robot arm. Clear? Moving on to the next one, that is centrifugal force. What do we mean by centrifugal force? That is, it generally is caused due to the appearance of the force on the outwards of the link when it is rotating around a joint. When any particular link is being rotating around the joint, it constrains with some amount of the force. So that particular force will be determined by the centrifugal force. Right? That is, in the context of the robot arm, as the link rotates around a joint. When the link is rotating around the joint, right? This particular force acts away from the center of the rotation. This force is been acting from the center of the rotation, which influences the stress on the joint and the required torque to maintain the desired trajectory. Right? Now, it is also significant in high-speed operations when the centrifugal force can become substantial and must be accounted for the control algorithm to avoid dissatisfaction. Next, moving on to the next term, that is Coriolis component. Coriolis component means it generally arises when there is a different parts of the robot arm which is moving simultaneously. When we have different parts moving simultaneously, then this particular component comes into action. Right? When different parts of the robots come into action, that is into motion, then this Coriolis component comes into action. It generally represents the effect of the velocities of one link on the acceleration of the another. Right? The Coriolis component generally represents the effect of the velocity of one link on the acceleration of the another due to the rotation motion of the system. This particular component is crucial in dynamic equation as it can cause additional forces. This will also cause additional forces where it is getting compensated for ensuring that the arm moves along the intended path without deviation. Right? Moving on to the next one, gravity term. Gravity terms also represent the force exerted by the gravity on the robot arm. Right? The gravity term also represents the force which is being exerted by the robot's arm gravity. This particular force must be countered to maintain or change the position of the arm. This is helpful to counter the change in the position of the arm, especially when the arm is vertical or in the inclined position. When the arm is in vertical or the inclined position, this particular gravity term becomes very useful to change the position of the arm. Right? And it also determines how much torque is required for the motor to support the weights of the arm and any payloads it carries. Right? If the particular end effector is carrying any sort of weights, how much weight it can withstand will be determined with the gravity term. Right? Next, moving on to the third discussion. Derive the equation of motion for a single link manipulator. Derive the equation of motion for a single link manipulator where we can use Lagrange's method, which is a systematic way to obtain the equation of motion for a mechanical system. Right? First, let us assume the length and the mass of a rigid body. First, let us assume the length and the mass of the rigid body. Now, when we are assuming the length and the mass, the link rotates about a fixed axis. Let us assume that, for example, we have z-axis, right? We have a z-axis. This particular link is rotating at a fixed axis, right? This particular link is rotating at a fixed axis. Now, the angle of rotation, that is theta, the angle of rotation, that is theta, acts on the gravity, acts downwards with the gravity, acceleration gravity. And the kinetic energy will be given as, the kinetic energy of the single link can be split into translation and rotation component, and the translation kinetic energy will be written as V is equal to L by 2 theta. That is, as per the center of mass of the link, right, as per the center of the mass, this, for example, this is the link. As per the center of the mass of the kinetic energy, this is being written as L by 2, right? So, the velocity will be written as per the center of the mass, the velocity will be written as L by 2 theta. And the translation kinetic energy will be written as T is equal to half mv square, which is nothing but the kinetic energy. Now, half m of what is V? L by 2 theta dot whole square, right? Where it will be written as 1 by 8 ml square theta dot square, right? This is for the translation matrix when it is in the translation motion. When it is in the rotational axis, T rotational will be written as half moment of inertia into theta square, right? half moment of inertia into t star square. Right? That is for the axis of rotation. For a particular uniform rod rotating about one end, I is been written as, the moment of inertia has been written as I is equal to 1 by 3 ml square, where t rotation will be written as, 1 by 3 of, 1 by 2 of 1 by 3 ml square into theta dot square, which is nothing but 1 by 6 ml square theta dot square. T rotation will be written when I is equal to 1 by 3 ml square, then the theta rotation, when we are substituting I value here, we will be getting half of 1 by 3 ml square into theta dot square, which is nothing but 1 by 6 ml square into theta dot square. Now, the total kinetic energy is nothing but T is equal to T trans plus T rotational, which is nothing but 1 by 8 ml square into theta dot square plus 1 by 6 ml square into theta dot square. So, this will be written as 7 by 24 ml square into theta dot square. Right? This will be written as 7 by 24 ml square into theta dot square. Whereas the potential energy, when we are determining, H will be taken as H is equal to L by 2 cos theta. Right? That is the height of the center of mass. The potential energy due to gravity is calculated by considering the height of the center of mass. That is, this is the potential energy equation. V is equal to mgh, where H is equal to L by 2 cos theta. And V will be written as V is equal to mg L by 2 cos theta. Now, as per the Lagrangian equation, we all know Lagrangian equation is equal to kinetic energy minus potential energy. So, what is the kinetic energy? T minus V. So, what we have got here, what is kinetic energy? It is nothing but 7 by 24 ml square theta dot square minus mg L by 2 cos theta. This is the Lagrangian equation which we will be getting. Now, we need to differentiate the equation of motion for the Lagrangian equation. Right? We need to differentiate the Lagrangian equation. So, that we will be writing as d by dt of dou L by dou theta dot minus dou L by dou theta is equal to 0. Right? When we are differentiating the Lagrangian equation, we will be getting d by dt into dou L by dou theta dot minus dou L by dou theta is equal to 0. So, what is dou L by dou theta? It is nothing but this 7 by 24 ml square theta dot square. Now, what is, so what we are getting? D by dt of dou L by dou theta is equal to 7 by 12 ml square into theta dot square. Now, we need to calculate dou L by dou theta. So, when we are calculating dou L by dou theta, it is nothing but dou L by dou theta is equal to mg L by 2 sin theta. So, as per the Lagrangian equation, 7 by 12 ml square theta dot plus mg L by 2 sin theta is equal to 0. Now, the simplified equation of the motion is theta dot plus 6g by 7l sin theta is equal to 0. Right? So, this is the equation of motion for a single link manipulator under the influence of the gravity. These are differences. So, in today's class, we have discussed about the single link manipulator using the Lagrangian's method, where we have calculated the kinetic energy first, and then we have calculated the potential energy. Then, with respect to the Lagrangian method, that is, Lagrangian method is equal to kinetic energy minus potential energy, and the differentiation of that particular equation, we have got the final equation of motion for a single link manipulator as theta dot dot plus 6g by 7L into sine theta is equal to 0. Right? And then we have discussed about the components, that is inertial term, centrifugal force, what do we mean by coupling inertia, what do we mean by gravity term, etc. And we have already also discussed about the kinetic energy, potential energy, and the joint velocity, which have been used in the robot arm dynamics. Right? So this is all for today. Hope you have understood today's session, and in the next session, we will be discussing about the discussion on question bank from module 4 and 5. Clear? Hope you have understood today's session. Thank you. Signing off for today, Dr. G. Hima Bindu.
Like, share and subscribe. Hit the bell icon for more updates.